In this video, you'll learn how plane frame elements are defined and how their stiffness matrix is simply a linear superposition of truss and beam elements. To begin with, we define what our element looks like and its degrees of freedom. So firstly, in the global coordinate system, we draw our element in an inclined configuration. With node I and node J. At node I, we now have 3 degrees of freedom, a horizontal displacement, a vertical displacement, and a rotational displacement. We label these as U3I minus 2, U3I minus 1, and for the rotation, U3I. So, for example, if node I was to be 1, then we would have U3I minus 2 would be U1, U3I minus 1 would be U2, and U3I would be U3. So it's just an extension of our labelling convention that we've been using for our truss and beam elements. At node J, we have the same degrees of freedom as we do at node I. So we have our horizontal, which is U3J minus 2, our vertical, U3J minus 1, and our rotational, U3J. The global horizontal axis is given by X, and the global vertical axis is given by Y. The inclination of the member relative to the x-axis is given by the angle theta. At the member level, so this is where our axes are parallel to the element, we have the following local element freedoms. So at node I, we have vertical displacement V bar I, horizontal displacement U bar I, and rotational displacement phi bar I. At node J, we have V bar J, U bar J, and phi bar J. Our member axes are then given by Y bar and X bar. The vector of elemental displacements is then U bar E transpose is equal to U bar I, V bar I, phi bar I, U bar J, V bar J, and phi bar J. To derive the stiffness matrix, we now need to consider the elemental strain energy. For a plane frame element, the stiffness matrix is given by the axial and bending strain energy contributions. So we may write that the elastic strain energy, lambda E, is equal to lambda E subscript A plus lambda E subscript B, where lambda E subscript A is the axial strain energy and lambda subscript B is the bending strain energy. The axial contribution in member coordinates is given by lambda E A, and that's, as shown before, equal to half times U bar E transpose times by the element stiffness matrix for axial members times by U bar E. From this we may write our term for K bar E A, and that is given by A E over L 0, 0 minus A E over L 0, 0 minus A E over L 0, 0 A E over L 0, 0. You'll notice that this is a 6 by 6 element stiffness matrix. This is because the rows and columns correspond to the total number of nodal degrees of freedom. These are indicated in red along the rows and columns of the matrix. So we have U bar I, V bar I, Phi bar I, U bar J, V bar J, and Phi bar J. Similarly, U bar I, V bar I, Phi bar I, U bar J, V bar J, and Phi bar J. You'll notice that the only non-zero elements in the axial elemental stiffness matrix are U bar I and U bar J. That is because our axial element only has a single degree of freedom per node. And those degrees of freedom are simply the displacements that run parallel to the member X bar axis. The other displacements are accounted for by the bending contribution to stiffness. To evaluate this, we consider the elastic strain energy for bending, which is given by lambda EB, which is equal to half times U bar E transpose times by the local element bending stiffness times by U bar E. In this, the element stiffness matrix for bending is given by EI over L cubed multiplied by the following matrix, which is simply the bending element stiffness matrix as we have previously derived. Again, another 0, 6L, 4L squared, 0, minus 6L, 2L squared, column of zeros, 0, minus 12, minus 6L, 0, 12, minus 6L, 0, 6L, 2L squared, 0, minus 6L, 4L squared. Again, I've written the local element degrees of freedom along the rows and columns of this matrix, and you can see here that the only contribution that the bending strain energy makes is to the vertical displacements and the rotational displacements. And these are given by these regions highlighted here. The plane frame stiffness is then the summation of the contributions from axial stiffness and bending stiffness. So we may write K bar E is equal to K bar A plus K bar B. And that then results in the matrix which just sums up equation 6 and equation 4. So when we add these two matrices up, we end up with the stiffness matrix for the planar frame element. In this matrix, I've indicated the axial contributions with blue ink and the bending contributions with red ink. The next step then is to transform this matrix into global coordinates. In the global coordinate system, each element has the following global degrees of freedom. UE transpose is equal to U3I minus 2, U3I minus 1, U3I, U3J minus 2, U3J minus 1, U3J. To move from the element coordinate system to the global coordinate system, we need to use the transformation matrix. The transformation matrix T, in this case, is defined as follows: sine of theta, cosine of theta, 0, minus sine of theta, cosine of theta, 0, 0, 0, 1, 0, 0, 0, similarly 0, 0, 0, 0, 0, 0, 0, 0, 0, cosine of theta, sine of theta, 0, minus sine of theta, cosine of theta, 0, 0, 0, and 1. As before, when we're moving from a local coordinate system to a global coordinate system, we pre-multiply our global element vector by the transformation matrix. So we may write U bar E is equal to the transformation matrix times by the global coordinate vector. So it is the case then that our element elastic strain energy is given by half times UE transpose transformation matrix transposed local element stiffness times by the transformation matrix times by UE, where T transpose K bar ET is our element stiffness matrix in global coordinates. It's usual practice when computing plane frame elements, because of the large number of elements in the stiffness matrix and transformation matrix, to independently calculate the transformation matrix T and the local element stiffness matrix K bar E, multiplying them together using a computer program such as MATLAB.